We'll see about the limit state method now. Limit state method. Limit state, in the name itself, it is the limiting state we are giving for your structure to be designed. Okay, limit state is nothing but the state of impending failure. First one, this method includes ultimate strength of structure, also the serviceability and durability requirements. We have two types of limit state methods. Two types. One is limit state of collapse. This includes, the limit state of collapse includes strength under flexure, shear, torsion. Fourth one is the compression. Second limit state of collapse is the second limit state is that limit state of serviceability. It includes, first one, deflection, second one, cracking, third one, vibration, fourth one, fire resistance, fifth one, durability. We have two types of limit states. Limit state of collapse, that we are checking for the strength under the flexure, whether if the member is a flexural member, we will check the strength for flexure, shear, torsion and compression. The limit state of serviceability includes deflection, cracking, vibration, fire resistance and durability. This is the long-term process which you are going to get for our structure. We ensure these two types of limit state under our design. Till now we are using limit state design for our structures. Now we are going to see about the analysis of sections under working stress method. Working stress method. Let us consider a beam of breadth B, total depth D. Consider this is the reinforcement is provided. Draw a center line from the top of the beam to the center line of your steel. This small d denotes your effective depth. From the small d till the bottom fiber, this is called as effective cover. From the bottom of your reinforcement and your section, this is called as clear cover. During the construction of this beam, we need to put a cover over that your steel is going to place. This is known as clear cover to ensure the durability conditions, because the water may enter into the concrete and it will corrode your steel structures. That's why we are providing the clear cover. Here from the centroidal line of the steel we are taking the depth. That depth will be the effective depth, then that cover will be the effective cover. Okay. The line in between your sections is nothing but neutral axis NA. What is mean by neutral axis? Axis at which stresses are 0, that is neutral, below which I am drawing a beam. When it is subjected to loading, it will induce deflection in this fashion, so that the top fiber will be subjected to compression, whereas the bottom fiber will be subjected to tension. So, when I draw the neutral axis, this is the axis at which the stresses are 0, that is neutral. Above part, this is compression, below part, this is called as tension. Okay. How to calculate the depth of your neutral axis? Here, I am giving x as the depth of my neutral axis. Above the neutral axis, I am calling it as x. X is nothing but depth of neutral axis. Here, I want to calculate where the neutral axis is being located. My first point, how to locate the position of neutral axis under working stress method. Okay, this is called as x. Now I can call this as d minus x. D minus x. If I draw the stress strain diagram of this concrete, when it is subjected to compression, this will be like that. The stress strain diagram I can draw in this same fashion here till only at the level of steel, not till the bottom. We are not interested in getting at the bottom stage of your stresses. Here, this is your sigma CBC. This is sigma CBC is nothing but stress in concrete under bending compression. This line sigma ST permissible stress in steel. Okay, now I can able to draw the diagram like this. At this level, I will get sigma ST, that is the tensile force, then I have a compressive force which is acting at the distance of 1/3, that is x by 3. So, the distance between C and sigma ST I can call it as Z. Z is nothing but lever arm distance. Now, I am going for the analysis part. Strain is directly proportional to depth. Here, breadth won't have any criteria in your design. It is mainly for fleshing your wall thickness in your structure. When we have a 130 mm wall thickness, you need to flesh your beam. For that we can increase the wall thickness or else we can decrease the breadth contains no major criteria in the design point of view. So, the strain is directly proportional to your depth. When we decrease our depth or when we increase our depth, it is being shrinked. That's why the strain is directly proportional to D. We can remove the proportionality sign. Epsilon C, this is strain in concrete. Epsilon C, strain in concrete, divided by x. This is this x. This is your sigma CBC, that is epsilon C. Strain in concrete divided by x is equal to strain in steel divided by d minus x. We can write this. Then d minus x divided by x is equal to epsilon s divided by epsilon c. Okay, here we can write this as m. M is nothing but modular ratio. So, d minus x divided by x is equal to sigma st divided by es divided by sigma cbc divided by ec. This formula comes from Hooke's law. So, d by x minus 1 is equal to sigma st divided by sigma cbc into ec divided by es. D by x is equal to 1 plus sigma st divided by m into sigma cbc, where m is equal to es divided by ec. So, x is equal to d divided by 1 plus sigma st divided by m into sigma cbc. So, I can call this as k. K is equal to 1 divided by 1 plus sigma st divided by m into sigma cbc. This is called as a constant value. K is nothing but a proportionality constant. Now I can call x is equal to k times d. This neutral axis depth x will depends upon your depth of your beam. It is being governed by the k, that is the proportionality constant. This proportionality constant is being governed by permissible stress in concrete and the permissible stress in steel. Okay. Now I can locate the position of the neutral axis where it is x or is equal to kd. Now the second part, I am drawing the beam of width b and depth d. This is the neutral axis NA. First one, strain block. When the load is being acted on this beam, you will get ultimate strain of sigma CB in bending compression. We have an ultimate strain of sigma ST in steel. Then I can draw the stress block. This is T. This is the tensile force being acted on the steel. This is the at the distance of x by 3. This is the lever arm distance Z. We can write sigma ST is equal to epsilon ST is equal to sigma ST divided by ES. Epsilon CB is equal to sigma CBC divided by EC. So, the tensile force is being acted along the region of your steel. T we can write it as sigma St, this is your permissible stress in steel, into AST. This is the formula. Then the compression force which is acting, which is being taken care by the concrete alone. Here we are not having any steel here. This compression part is being taken care by our concrete. So the compressive force C we can write it as, being this is the triangular fashion, the area of triangle is half into base into height, half sigma CBC, the height is x times your breadth of your beam. So this is the formula for T, sigma St into AST. C is half sigma CBC into XB. Equilibrium of horizontal forces. We can equate, to maintain the beam under equilibrium section, T should be equated to C. Okay. Here we all know X is equal to KD. T sigma St into AST is equal to half of sigma CBC into X into B. Here for this X we can write it as KD. If you want to calculate the depth, we can calculate from this method. We all know about the design constant sigma St, sigma CBC. When the AST is being provided, we can able to calculate the depth of your section. Okay. Next one, moment of resistance. To calculate the moment of resistance value, we need to calculate moment of resistance due to steel and the moment of resistance due to concrete. For that, we should have something, lever arm distance Z. We can take it as D, this is D minus X, D minus X by 3. Here this distance, this is the depth, total depth small d, that is your effective depth, minus X by 3. So here we can call it as D minus X, we can write it as KD divided by 3. So Z is equal to D into 1 minus K by 3. This 1 minus K by 3 we can call it as J. So Z is equal to JD. So we will get two constant. The lever arm, we have a constant called as J, it depends upon your depth. Then we have a neutral axis depth X, which depends upon your K, the proportionality constant. Based on these two values, we are now going to calculate the moment of resistance of a section based on MS and MC. Moment M is equal to, we can take it from T times JD. We can take T times JD, or else moment of resistance due to concrete, that is C times Z or C times JD. Here we can write FST, AST into J into D. Here half sigma CBC B X into J into D. Here we can write it as half sigma CBC B J D. X we can write it as K into D. That's why half sigma CBC K J B D square. So this value is being a constant value, we can call it as R. This is called as moment resistant coefficient. R into B d square. So, the bending moment is equal to R into B d squared, where R is your moment factor, we can call it as moment factor, or else moment resistant coefficient we can call. Equating T is equal to C, sigma St AST is equal to half sigma CBC B into KD. Here AST divided by, take this BD here, BD is equal to half of sigma CBC divided by sigma ST into K. We can call this AST divided by BD is equal to percentage of steel. We can notate in the letter P. P is equal to AST divided by BD. So, the percentage is equal to half of sigma CBC divided by sigma ST into K. This is also called as reinforcement index. For a particular section of beam B into D, what is the percentage of steel is being provided in the beam? This is called as reinforcement index, or we can write as sigma CBC divided by sigma ST is equal to 2P divided by K. This is the next thing. Then we are telling that in working stress method the strain is being linear. Strain is linear. Sigma CBC divided by epsilon ST is equal to sigma CBC divided by EC divided by sigma ST divided by ES, that is sigma CBC divided by sigma ST into modular ratio. Similar triangle method. Epsilon CBC divided by epsilon ST is equal to x divided by d minus x. This we can call k divided by 1 minus k. FCB divided by F sigma CBC divided by sigma ST into m is equal to k divided by 1 minus k. Sigma ST is equal to m into sigma CBC into 1 minus k divided by k. Sigma CBC divided by sigma ST into m is equal to k divided by 1 minus k. Sigma CBC divided by sigma ST is equal to 2P divided by K. It is in the form of reinforcement ratio. Now we can equate this equation 1 to the equation 2. 2P divided by K into M is equal to K divided by 1 minus K. 2mp into 1 minus k is equal to the k square minus 2mp into 1 minus k is equal to 0, where we have known equation for modular ratio. M is equal to 280 divided by 3 sigma CBC. When the grade of concrete is given, we can directly calculate the sigma CBC value from the IS 456 code. Okay. From the IS 456 code, table number 21, the permissible stress in concrete, when the grade of concrete changes, we'll take sigma CBC value. This is for bending compression. When for flexural members, we can take this sigma CBC values for M10 to M50, and this is for sigma CC is for direct compression values 2.5 to 12. Then this is your bond stress average tau BD values from your code book of table 21. Analysis of section in bending. This is our section B. This is our reinforcement provided, neutral axis. This is called as KD. B times KD into KD divided by 2 is equal to P by 100 into BD M into D into 1 minus K. Here K square plus P by 50 M into K minus P by 50 M is equal to 0. From this equation, we can solve this equation. Minus B plus or minus root of B square minus 4AC divided by 2A. We can get where P is equal to 100 AST divided by BD. Moment of resistance M is equal to P divided by 100 into BD sigma ST D 1 minus K by 3. M divided by BD square is equal to P divided by 100 1 minus K divided by 3 into sigma ST. This is what we are going to have the moment of resistance for a section when we have percentage of steel provided. Types of sections. First one, consider a beam having the neutral axis. We will have the stress block like this. Then for the types of sections, we have 3 types of sections. It is purely based on the neutral axis value. First one, balanced section. Balanced section is that for RC section, when the allowable stress in steel and the allowable stress in concrete, at the same time it will gives you the optimal section of your neutral axis. When the steel also yield, the concrete also yield, when it behaves in same fashion, you will get the optimal neutral axis section. The moment due to the concrete failure and due to the steel failure, both are at the same time. This is called as critical or balanced section. Okay. Next one, under reinforced section. Here the name itself, it is under reinforced. It is not exactly balanced. The concrete is more when compared to the steel. We are putting less amount of steel for this section, so that when we provide less amount of steel, the steel will first yield, after that the concrete will yield. So the steel failure will proceed faster than the concrete, because it will gives you some warning before failure of your structure. the stress curve for this is the strain value. This is called as, here this line is called as under reinforced section. This line where it touches, this is called as over reinforced section. Third one, over reinforced section. So the strain for the balanced section is sigma y, whereas this under reinforced section we are putting less amount of steel, so steel fails first before the concrete is subjected to failure. So the under reinforced section, your strain value is greater than epsilon y. Okay, let me come to the over reinforced section. The over reinforced section is that we are putting more amount of steel so that concrete yield first. Here the over reinforced section will be subjected to brittle failure, whereas under reinforced section will be subjected to ductile failure. It will gives you enough warning before collapsing of your structure. That's why we are mostly using under reinforced section for our design point of view. The balanced section, it is not predictable exactly the value. That's why we are not clearly says that the concrete also yield in the same way the steel also yield, so that from the balanced section we are comparing these two, under reinforced section and the over reinforced section. Over reinforced section, most of all we are not using it in our structures. Mostly the structure designed as per IS 456-2000 or under reinforced section alone. We are putting less steel when compared to the other sections. This is what the analysis of working stress method is all about. Today in this lecture we have seen about the design methods. We have 3 design methods and how to analyze the sections of RC under working stress method alone. In the next lecture we will see about the singly reinforced and doubly reinforced sections. Thank you.